T-minus 20, still counting at this time. We have ignition sequence start. 6, 5, 4, 3, 2, 1, 0. We have ignition.
Attention, all programs started. Our vehicle going now to enhancement heading of 72 degrees. All 5 F1 engines starting.
Good morning and welcome to the ATCO SpaceLab Speaker Series. My name is Claire Porbay and I'm a platform specialist with the transformation team at ATCO, and I'll be your moderator today. I'd like to begin by acknowledging the Indigenous peoples that are traditional custodians of the land that I am on today. While this is a virtual platform, I will take a moment to reflect on the meaning of place, and in doing so, recognize the various traditional, ancestral, and unceded lands on which ATCO conducts business. I do this to reaffirm my commitment and responsibility in improving relationships between nations and to improve my own understanding of local Indigenous peoples and their cultures. I am honored to live and work in Treaty 7, the traditional territories of the Blackfoot Confederacy, Niitsitapi, comprised of Siksika, Kainai, and Piikani nations, the Tsuut'ina Nation, and the Stoney Nakoda, including the Chiniki, Bearspaw, and Goodstoney First Nations. The city of Calgary, Mohkinstsis, is also home to the Métis Nation of Alberta Region 3. I would also like to pay my respects to elders, past, present, and upcoming, in the communities and regions where we operate. Our speaker today joins us from Irvine, California. The UC Irvine campus is located on the homelands of the Ahashiman and Tongva peoples, and I'd like to recognize all their ancestors and descendants, past, present, and future, who are the original and current caretakers of the land, water, and air. I want to thank you all for joining us for our fourth ATCO SpaceLab Speaker Series event of 2023. Today's lecture is a one-way video and audio format. There'll be time at the end of the lecture for questions, and you can ask questions by using the question icon at the right of your screen. For an optimum viewing experience, we also recommend closing all browser windows and any unnecessary programs. These lectures are a chance for us to share knowledge and insights from thought leaders, providing our ATCO colleagues and ATCO's network of peers, partners, and friends with information on promising developments, trends, and leadership in exciting and relevant fields. We previously heard from Dr. Maxim Bazanov from the University of California, San Diego on June 29th. If you missed Dr. Bazanov's lecture, you can visit ATCO's YouTube channel to watch a recording of the event. If this is the first time you've heard of ATCO SpaceLab, I am so excited to tell you more. SpaceLab was established in 2019 to reinvigorate ATCO's entrepreneurial spirit and to support our colleagues in pursuing challenging opportunities outside of the scope of their day-to-day activities. Today's SpaceLab is an environment where any ATCO employee may achieve new creative, innovative, and future-focused results for ATCO. And in addition to presenting this lecture series, SpaceLab also offers a learning series, the Community of Action, and is a source of funding and a specialized expertise for ATCO employees to execute their innovation projects. Since the fall of 2019, over 130 projects have been initiated as part of SpaceLab. Today we are joined by Dr. Plamen Atanassov, Chancellor's Professor of Chemicals and Biomolecular Engineering, Material Science and Engineering, and Chemistry from the University of California, Irvine. The list of our speakers' accomplishments is extensive, and in the interest of time, I'll mention just a few awards and honors our speaker has received. Dr. Atanassov is an honorary professor of the Bulgarian Academy of Sciences. He is a fellow of the International Society of Electrochemistry and the president-elect for the society in 2023 to 2028. He is also a fellow of the Electrochemical Society and has been inducted into the National Academy of Inventors. Today, Dr. Atanassov will present a conceptual path to enable net zero emission energy systems and improve human health and prosperity by transforming the chemical, manufacturing, and energy sectors through electrochemical engineering of hydrogen, carbon, and nitrogen cycles. This topic is of particular interest to ATCO as we continue to pioneer innovative energy solutions and focus on enabling the transition to a net zero emissions future. I am so pleased to welcome you, Dr. Atanassov, and we look forward to learning from you.
Well, thank you very much. It's really an honor to be here with you. I've never participated in a industry organized broad learning and outreach series, and it's a new experience for me as well. So hopefully it will be interesting. I have worked with industry all my life. but mostly as an academic who is targeting technology transfer engagement and building projects under different governmental and direct industrial funding. So hopefully this set of thoughts will be of use for you as colleagues and partners and potential future collaborators, and maybe it will inspire some thoughts and questions. Thank you. So the topic and the claim is that electrocatalysis as a general set of projects or methods or processes that are engaging electrochemical systems in energy conversion, storage, and power generation devices is a key enabling technology for decarbonization of the Earth economy. I am proud to speak on behalf of my colleagues at the University of California, Irvine, and we work on several programs, large and small, and I will mention a couple of them as I go through my talk. So, first of all, I would like to start with the acknowledgement that the actual global warming, whether it's believed by some that it's naturally caused or believed by many that is being caused by human activity, is a fact that will inadvertently change our lives as society. And we should actually do more to intervene as community, as nations, and as global society in working towards achieving global warming curtailing targets, mostly within the decreasing of carbon dioxide direct emissions and reformatting the technology to avoid using fossil fuels and to avoid using heat sources when possible for energy transformation. So these are recognized targets by organizations as large as the United Nations, by groups of nations as the European Union, and individual nations like United States and Canada, Japan, and today even China and India. So I am coming to give the concept of reducing of carbon dioxide footprint that heavily relies on the production of renewable electricity with sources that do not emit CO2, becoming today probably and will be staying in a near future as most economically efficient, viable energy source, or power source actually, energy transformation technology. So these advances in the physics and technology and material science that allowed the deployment of the solar panels at huge scale and low cost, and the wind turbines at huge scale and low cost allowed actually the production of electricity from those sources to become currently the most desirable investment act in new energy technologies. The clear gain actually is associated with gaining power usage for nations without decreasing their developmental and utility indexes. That's the critical target, because we can talk a lot about decarbonizing societies that are way ahead in the developmental indexes, but the human mass and production of CO2 by China, India, and societies like which will emerge on the African continent, technological societies of the next century, will be the ones to determine whether or not we will succeed with cooling or stopping the warming on Earth. Practically speaking, it is very important for us to develop and deploy technologies that will be easily adaptable by others. It will be easily adaptable by countries like China and India within the realm of their production capabilities and intellectual ownership rights, so they will be decarbonizing themselves as soon as possible. So in that sense, the United States, Canada, even the European Union present actually the flagship or trailblazer or technology demonstration cases, but technology implementation should be carried by societies like China and India to become really, really impactful on global scale. The European Union was the first major market that embraced hydrogen economy as a societal impact strategy for decreasing of carbon dioxide emissions. Technologically speaking, Japan, as a relatively small market, had the first steps in that direction about 8 years ago, but the things became globally impactful when European Union adopted strategies 4 years ago that essentially put the national hydrogen strategy of Germany in June 2020 in the core of the European legislation that followed the next year. Yeah, this national and European Union economic strategies were expressed in the form of hydrogen economy investment and roadmaps that declare different sectors of hydrogen economy as immediately available for deployment or related to capital return of investment. It's very interesting that this morning, United States actually, Department of Energy had a major webinar discussing the features of the American roadmap for hydrogen economy, which I couldn't put in this presentation just because I had to submit it yesterday. You see how important it is to be actually on the spot and on the money. This morning, 7 o'clock a.m. California time webinar in Washington, D.C. enriched actually the thought process because it declared the American goals in deployment, reduction of cost, and on the programmatic funding, which I'm going to come to talk a little bit later. The decarbonization goals were recognized by the Biden administration from the moment it's coming to office. And it was the first administration that actually followed the academics' incentives and the academics actually, projected goals. And it actually built its national decarbonization strategy based on a report from the National Academies of Science, Engineering, and Medicine. It may look to you very obvious as a way of establishing national goals, but it happened for the first time in 2020. These are very ambitious goals, and they are difficult to achieve. But to get there, the set of so-called earth shots were proposed by the Biden administration through the Department of Energy Secretary Granholm. So the first earth shot was the earth shot related to hydrogen. And it was very easy to be declared as a $1 per 1 kilogram of hydrogen achieved within a decade. Technically speaking, that's not that difficult if you just want hydrogen, because the current cost at the well for hydrogen developed from methane stem reforming in the United States is $1.53. What really this means is that we need to actually make the hydrogen through renewable electricity and renewable ways, including pyrolysis. The commitment here is that the current amount produced of hydrogen in the United States, which is 10 million metric ton per year, should be achieved fully decarbonized by 2040. So essentially, by 2030, which is only in 6 years, we need to be able to produce the 10 million metric ton of hydrogen exclusively from renewable sources and pyrolysis, or from the sources that are offsetting the carbon footprint. And by 2030, 20 million ton, double it, and by 2050, 50 million tons. and that corresponds approximately to essentially covering all the needs of major transportation, excluding the personal transportation, and all major needs of the industry provided by the hydrogen. So that's a very steep national target that was revealed this morning. And here I'm just setting the onset of that, the conceptual schematic of the hydrogen at scale, which was developed at the National Renewable Laboratory in Golden, Colorado, 8 years ago, that set the intellectual notion towards the hydrogen economy. The deployment of the hydrogen economy has started with two major legislations in the United States. The bipartisan infrastructure law that set aside $9.5 billion for hydrogen research and deployment. 7 of them will be distributed within the next month into 6 to 10 regional hubs. One will be also distributed close to the beginning of next year for interconnecting projects, and $1.5 billion is being currently competed for lower TRL level research by national laboratories, $800 million, and the universities and industry, $700 million chunks. So these are the current direct investments in hydrogen economy, like a priming the hydrogen economy in the United States. And then it is followed by the infrastructure, the infrastructure law is followed by the Inflation Reduction Act. And the IRA provides $38 billion in tax incentives for industry that will pick up hydrogen deployment. So at any, that the United States, there is no clearly defined tax rate for industry, but you can assume that's about 22% for manufacturing industry. So it will make you expect 160 to 170 billion dollars of hydrogen economy worth by the progression of that act, which is 7 years from now. So those two laws set the stage of priming the hydrogen economy through the hubs that are sets of projects, and for essentially developing further the hubs through a national investment and banking engagement, and through the recovery of the tax. This creates a very different way of engaging the hydrogen economy in the United States than in Europe and in Japan, and definitely very different from the one proposed for China. So the hydrogen hubs were competed, and the competition completed by interviewing of the 13 finalists, from which 6 to 10 will be awarded in September. I was honored to be a part of the California team that created the Alliance for Renewable Clean Hydrogen Energy Systems, called ARCHES, and that is the California hub that is a finalist, and we completed our final rounds of discussions with Department of Energy last week. Now we wait. I will give an outline of the ARCHES at the end of my talk, if you're interested to know more about what California as a state proposed to the Department of Energy for the hydrogen deployment. The very specific needs of hydrogen are related to decarbonizing components of the economy that are extremely difficult to decarbonize otherwise by direct electrification. Sometimes people associate hydrogen economy with hydrogen fuel cell cars, and they think about Mirai and they think about Hyundai Nexo, which are wonderful demonstrations and early adaptations of hydrogen technology. But the truth is that the real competition is not between the battery-powered vehicles and fuel cell-powered vehicles, on the passenger car scene. The true competition in the transportation is actually in the trucks and the ships and the planes, and I will show that a little bit later. The real impact, however, where we do not have any other ways but decarbonizing the chemical industry through using of hydrogen today. So essentially replacing a carbon footprint heat sources and carbon footprint chemical sources with the hydrogen as a reduction agent and as a power provider for ammonia synthesis, for steel and cement. If you look at these difficult to decarbonize sectors, the steel and cement and ammonia account for approximately the same amount of energy consumption as all the transportation in the average country. So decarbonizing those sectors is critical for the arrival of the CO2 footprint minimized or decarbonized technology. The way we're looking into decarbonization of the industry in transportation is by mentally engaging in these three major cycles. It's the hydrogen cycle, the carbon cycle, and the nitrogen cycle. The hydrogen cycle is related to water as the major source of hydrogen, and the splitting of water happens in electrolyzers. Water electrolysis can be supplemented, of course, by pyrolysis of biomass with a capture of the carbon in a solid state in that pyrolysis and releasing hydrogen, and in many cases CO as a byproduct. So the hydrogen produced by electrolysis is definitely a process that is electrocatalytic. Then utilization of that hydrogen in fuel cells to provide electricity is definitely an electrocatalytic process. So in addition to that, currently there are several programs to use electrocatalytic processes to drive electrolysis reactions in colloidal dialysis cells to make a clinker component of the cement. And that's the way to afford lowering the temperature signature and thus CO2 signature of a cement manufacturing. We can directly capture with electrochemical process CO2 either from concentrated sources like industrial sources like pyrolysis including or air, and then convert it to a CO as an active intermediate for chemical synthesis, or valorize it either electrochemically or in a combination of electrochemistry and chemistry, or electrochemistry and biotechnology to produce value-added products that start probably the easiest way to think of it. It starts with ethylene oxide as a major stock feed in the chemical industry. And then the nitrogen cycle that heavily relies on a Haber-Bosch process to essentially activate nitrogen and turn it into ammonia. The direct decarbonization of that process is currently possible by engaging hydrogen that is made electrocatalytically, as opposed to in situ generation in the plant of hydrogen from methane stem reforming and using part of the hydrogen bleed to heat the system. But there is also futuristic ways of engaging nitrogen from atmospheric air by cross engaging with CO from CO2 or CO from industrial sources and directly make urea. And I will show some examples of that. So all of these processes can be exercised in electrolyzers or fuel cells, and all these processes are electrocatalytic. So if we deploy electrocatalysts, or if we do research in electrocatalysts and TRL level from 1 to 3 or 4, we will be enabling these major industries to be arising above the TRL level 5 over the next decade to take a major participation in decarbonization technologies. So the current snapshot of where we are with water electrolysis is given here in this diagram. This diagram is created at Jülich, which is the like the national lab in Germany, and that's why it's presented essentially in euro. But in every economic environment, similar diagrams exist that relate the cost of hydrogen production and the operational length of using electrolyzers for two particular devices. The upper blue line shows, let's say, boutique, expensive device that is probably more efficient, has a less footprint, like PEM electrolyzer. And the bottom line is, let's say, a deployable traditional device like alkaline electrolyzer. And between them lays the developmental area in a blue kind of a background in this diagram that shows you the cost operation space for water electrolysis. On the top of that, we project the cost, the operational requirements and cost compatibility for major technologies that are being discussed today in a hydrogen economy. And we can see that hydrogen as a fuel for fuel cell electric vehicles and hydrogen used in industry as a feedstock, my 2 points in this lecture, are actually a business. They can make money. Everything that falls out of the blue segment, like the power to heat, power to synthetic natural gas, and power to gas and back to power, are outside of that design window. So we will need, in order to consider them included economically, we will need to either lower the cost and of the hydrogen production, essentially pull down the curve, or increase the viability of these energy technologies to be included there into that curve. So bottom line is that these three types of technologies will need assistance from the government, either through incentives or through credits, or otherwise direct investments in research to modify them and to bring them in. Or they will remain outside of the immediate business for the deployment in the next decade, as being essentially losing. So please bear in mind that what is not losing is transportation and chemical industry as a decarbonization effort for hydrogen. So in the transportation sector, here is a diagram that actually was adopted from a Toyota report that shows you that there is absolutely no reason to compete with the light-duty vehicles for short distances in urban areas for hydrogen cars, because that market is captured by lithium-ion batteries through their versatility and low expense and their integration with vehicles that is in a way seamless. The only problem is that if we start moving up to the demand in terms of power and energy, they simply cannot measure up. So the battleground is between medium to high duty vehicle, when hybrids of various kinds, including a hybrid with a hydrogen vehicle and hydrogen traction and electric vehicle is most likely be dominating, particularly vans, and hydrogen fuel cells will be the only visible propulsion power in trucks, especially in the lorries when they are 18-wheelers and that what's called Class 8 trucks in the United States. It has been also recognized that anything on the upper right hand of this diagram going towards trains and ships will also need to use either hydrogen or hydrogen derivatives, including aviation, because the energy density is not comparable to the lithium batteries that you can fly. So you can clearly see that in the deployment and demonstration of the hydrogen vehicles in American ports, particularly in California, when essentially access to the ports by vehicle trucks for cargo in and out, and drainage in the ports and port lifting and moving is critically important as a local so local need of energy, and the diesel that is used en masse is a major source of local pollution. So that's important to note that these technologies are coming also to address important social causes of pollution, and I'll come to that a little bit later if time permits or if you have interest. The fuel cell electric vehicles in the classes of the trucks that are essentially 18-wheeler trucks and class 7, class 8 is such that the competition there with gasoline is reasonable in both pricing and the size of cargo space when you exclude the fuel and the auxiliary components of the engine. And for battery electric vehicle, it becomes prohibitive to operate a vehicle larger than the size of a pickup delivery one for intermittent operation, which means operating only in the day and charging at night or whatever the cost of electricity is lowest. The real-time use in fleets will most likely be the first to use hydrogen en masse, and those fleets for either service vehicle in a constant use, like Amazon delivery trucks or postal office delivery trucks, and fleets of vehicles in and outs of ports and long-haul trail through the country. In the United States and in Canada, the long-haul with trucks dominates the transportation, and as you probably know, the electrification of the long railroads is also not fully completed or not possible because of the losses in the very long distances. So countries like United States, Canada, China will be compensating for that by using fuel cell driven locomotives in their long haul railway systems. So I just wanted to demonstrate to you when is the breakdown of the fuel cell power system cost and cost of ownership for a car is much lower than the cost of ownership for a truck. So the cost of ownership for a truck is around $200 per kilowatt used electric, which is very comparable to what we have with the current cost of ownership of diesel vehicles, and the cost of ownership expectation for light-duty vehicle in the United States is somewhere around $40 to $50 per kilowatt electric. In Europe and in Japan, it's about 75 dollars per kilowatt electric. So the reality is that that's why you see Japanese fuel cell cars and Korean fuel cell cars, and you don't see yet on the market American fuel cell cars, although prototypes were available 20 years ago. It's just the cost of ownership in the United States, because of the cheap gasoline, same as in Canada, is extremely low for the gasoline vehicle, and the competition is practically impossible for the fuel cell vehicle. But at the moment you move to trucks, it becomes affordable, and it actually becomes technically and economically viable to make that transition. The transition for the fuel cell trucks was discussed by the Department of Energy. I'm just giving you an example how Department of Energy in their programs discusses the reduction of cost by what we call, as a slang, the waterfall diagrams. It identifies which individual processes and which individual targets can contribute to substantial cost reduction. And here you can see that from the current $323 per kilowatt for the 275 kilowatt system for heavy duty vehicle, how we can account for reduction of individual components in costs to reach what is needed to make the ultimate target of DOE of $60 per kilowatt. And that's the cost target at the production. So then you can sell with profit and you actually can have an economy at that level. So the cost of ownership parity is achieved at approximately 200, and then you can actually deploy as a demonstration. And then in order to actually have a business, you need to have a difference between cost of ownership and the production cost. So you can actually make money by making and selling these things. So, and each of us is finding how to participate in these programs, because the individual projects are issued, FOAs, these are the calls for proposals, are issued to address individual targets in this diagram. I have a privilege of working here at the University of California, Irvine, with notable colleagues that are directing Fuel Cell Center, California Clean Energy Institute, just founded this year, and Horiba Institute for Mobility and Connectivity, that looks about the car's integration with electric powertrain systems. That gives us a wonderful opportunity to have research starting from atomistic scale to material scale and the integration of this into essentially layers, functional components, and then devices, and devices into stacks, and then into real systems. All of it is possible here academically. My principal contributions have been in the design of electrocatalysts for either electrolysis cells or fuel cells, both in alkaline and in acidic environment. And my major contributions are in making essentially designer materials, when the catalysts will be envisioned as based on knowledge that we receive from biological catalysis, get inspired by it. I wouldn't call it just copying, it's not biomimetic, but bio-inspired catalysis. Then we implement in materials design, either in clusters or particles, in graphene sheets, and in composite materials that contain multiple layered materials for reactivity. It's very important to note that when you design electrocatalysts, you need to be taking care of the materials design at the hierarchy of scales, because the processes happen not only and solely on the interface at the atomic level, but you need to also critically introduce the reactants to the reaction zone and withdraw the products without hindrances in that process, or with minimized hindrances. The majority of the losses in practical electrochemical devices are actually heat losses that has to do with the transport to and from the reactive media. And the design at every level is critically important to accommodate for those losses. So not only you need to design for the reactivity at the interface, but design a hierarchy of scales for all the transport processes that happen within the immediate proximity of the catalytic particle. Again, I'm coming to remind you about the diagram that I have posted on different cycles, and to show you that here at the University of California, Irvine, we're actually working on each and every one of these potential electrochemical units of operation. They're at different TRL levels. Some of them are just very juvenile, and some of them are very, very advanced. And I've been contributing to several of these processes through my career, back at the University of New Mexico through the 27 years, and now 5 years at the University of California, Irvine, by providing catalytic materials for those. The catalysts that are designed for operation in fuel cell for heavy-duty vehicle are currently being integrated in several programs under the consortium called Million Mile Fuel Cell Truck, or M2FCT. That's a Department of Energy consortium that is led by Los Alamos National Laboratory team and Lawrence Berkeley National Lab team, with the participation of several colleagues from industry and few colleagues from academia. We're very lucky to be among those. So we design platinum and platinum alloyed catalysts that are with a specific shape and activation at nanoscale, and we integrate these catalysts with supports, carbonaceous supports with a special design to afford exactly for those transport processes. And such catalysts are expected to perform with the necessary power generation, as evidenced by these polarization curves, but also they need to perform with stability and durability as required for the Department of Energy to meet in simulated environment a 1 million mile effective durability with a drop of no more than 15% of their activity. And that will allow essentially the utilization of such catalysts in heavy-duty vehicle. That is associated with design of supports that do not corrode, and one approach is to use supports that are based on conductive metal oxides, and my laboratory specializes in designing of carbon supports with the highly graphitized carbons and conductive metal oxide supports that are also not susceptible to corrosion. So this illustrates a collaborative effort between my lab and the Cabot Corporation, and also colleagues from Colorado School of Mines, and a company called Bosch. Probably you know who Bosch is, and you know who Cabot is. Cabot is one of the major players in the carbon and oxide materials, and Bosch is the largest non-publicly owned company in the world. The largest non-listed company on any stock exchange, so to speak, in the manufacturing sector, of course. So we work with these partners to develop carbonaceous materials that will be specifically oriented with their graphitic sites towards the interface to minimize the actual corrosion by structural mitigation. We also are known for the development of non-platinum catalysts for fuel cells in order to alleviate the dependence of platinum sources, which probably you're aware are extremely rare and extremely concentrated outside of the United States and Canada. The platinum sources are 75% within South Africa and 20% within Russia, with one very small amount of produced in US and Canada, and just a little sliver in Brazil. So the non-platinum catalysts that we have developed through the last 20 years are from the family of the so-called transition metal nitrogen carbon materials that are graphitic-like structures that have transition metal, that let's say iron, that is being incorporated in a nitrogen-doped carbon, and those materials allowed essentially oxygen reduction reaction in alkaline media comparable to platinum, and oxygen reduction reaction in acid medium with an activity of about 1/3 of that of platinum, being inferior to platinum by a factor of 3 only. So it's very difficult to compete with platinum, which is the kind of a God-given catalyst that does it all. So over the last few years, my student Eamon Murphy, who just graduated and literally starting this week at Los Alamos National Laboratory, had developed a whole a whole series of atomically dispersed catalysts from this series, from this type, when you have a transition metal incorporated with nitrogen and carbon in the carbonaceous matrix. And these materials actually allows us to do catalysis in various, very different environments outside of just oxygen reduction, but look at these materials as a prototypical catalyst for a lot of chemical reactions that can be carried electrochemically. So to do that successfully, we have shown that we can make this catalyst with approximately the same or controllable structure and to display the atomically resolved individual atoms. 6 of these materials are just for the first time reported ever in the literature. That's why it was published last week in the Nature Communications for everybody to see that. We have demonstrated the use of these materials in a subset of the nitrogen cycle, essentially synthesis of ammonia from nitrates, which is a component reaction in the overall synthesis of ammonia from nitrogen after activation of nitrogen. In the perceived alternative to Haber-Bosch process, one can activate nitrogen to nitrates by high-frequency controlled plasma, and that essentially can capture those nitrates after the plasma reactor and carry it to ammonia electrochemically. So we have shown that we can have different atomically dispersed catalysts to selectively produce ammonia from nitrates and nitrates, NO3 minus and NO2 minus, and by introducing different atomic species, either iron or molybdenum, we can regulate the selectivity between these two processes. That further was extended, as I told you in this Nature Communication paper that came last week, of actually screening the entire library for nitrate reduction, one of the most complex electrochemical synthesis reaction, nitrate reduction to ammonia, and showing that several of these catalysts demonstrate extremely high Faradaic efficiency for ammonia synthesis. In similar fashion, you can look at the CO2 reduction, which is also a complex schematic of reactions that can be integrated with bioprocesses for further valorization, and you can employ catalyst for making essentially selectively CO and hydrogen from this feedstock of CO2. We have studied this catalyst extensively, understood the mechanism of operation, and through that mechanism designed and proposed. I'll just skip a few slides in order to be able to show you some more about California. We have shown the role of morphology of these catalysts, and we have also shown that we can, by design parameters, obtain a specific ratio between CO and CO2. So essentially, between CO and hydrogen in the effluent from clear, neat CO2 in order to produce controllably a syngas of a ratio that is desired by industry. That was the work of Laurent de Lafontaine, another PhD student of mine that graduated this year, currently working for a consulting company called Exponent. This thing can be taken further and used in conjunction with valorization of the CO2 reduction towards making of a formate. Formate is critically important because there are many fermentation processes that start with formate, and also it's a relatively expensive chemical product from which chemical transformations can be taken. As an example of us taking also a step further and designing a reaction for obtaining of acetate and 1-propanol, normal propanol, electrochemically from CO2 and CO. All of this is happening in electrochemical reactors in my laboratory, and I would like to acknowledge my students. I don't have a very big team, but as you can see from the bottles behind me over there, these are the bottles for the PhD defenses, and only this year we had 4 PhD defenses. Everybody is successfully employed before the dissertation is over. So I will actually give you here a few thoughts, if I can, about the role of the electrocatalysts in hydrogen economy. They're solving critical reactions. My laboratory is only one of many that contributes to this with solutions, which I believe are original, but we are not the only one working in this area. Now, I have about 10 minutes left, and if you allow me, I would like to show you just a few like strikes about the ARCHES, which is the Alliance for Renewable Clean Hydrogen Energy Systems. It's the California Hydrogen Hub. I was among the few people that started the initiation of the hub 2 years ago, and then stood with my colleagues from Berkeley National Lab and the University of California system when all 10 campuses joined with the Office of Business, California Office of Business and Innovation, and then brought in 3 major labor unions, all the tribal societies in California, the cities of Long Beach and Los Angeles and cities of Oakland and their corresponding ports, as well as another 6 smaller communities in California, to engage in a public-private partnership that embraces the entire state of California with the goals of decarbonizing the port and heavy-duty transportation. And the Andy Warhol diagram on the lower left corner that you can see was my implementation, or actually it's an emblem that I created to show the government that the Environmental Justice 40, which is a law in the United States, can be served by the ARCHES hub by practically coinciding of our hub activity with the disadvantaged communities, the communities that suffer from air pollution, and the people who have lower than average income by 1 sigma and lower. So that shows you that the California hub serves particularly the environmental justice and decarbonization targets at the same time. The actual production and distribution activities are between 4 subregions: the North, and then the North Valley, Northern California around Bay Area, North Valley, South Valley, and Southern California around the Los Angeles basin. We particularly pay attention in decarbonization of the activities in the ports. The 4 major ports in the state of California are responsible for 48% of the freight of the United States international trade by sea, and in a ton ton expression, and about 58% in cost figures. So the hub is created grassroots up. It's actually had its own screening process to identify 39 projects that were engaged in the program with Department of Energy, and there is 31 projects that are not engaged with Department of Energy but are engaged with the state of California. So it's a 2-layer hub, and that's a network of programs that will bring us to 16 million ton per year in 2045 as a trajectory. So I just want to remind you that at that time, United States is targeting to have 45 million tons per year, which shows you the disproportionately high component of contribution of California to the national hydrogen outtake production. It's also is very important to note that the production is balanced with outtake, and we have this shown regionally and shown also by demand and supply diagrams of how the outtake will be balanced with the production by 31, which was described in the project. And the right-hand side shows you the flow of the production from Northern California, North Central Valley, South Central Valley, and Southern California into the different usages of the three major outtakes, the power, ports, and transportation. And by transportation, we mean here heavy-duty transportation. So the way it is organized, it relies on electrolytic production of hydrogen for about 80%, between 80 and 85%, and 20 to 15% of production by pyrolysis of bioproducts and agricultural waste. So these two streamlines are then intermittently stored for production and distributed by pipelines or by trucks, and then used in the hub primarily for off-load leveling of the grid to decarbonize the grid, and transportation and the ports. And the transportation is heavily associated with the urban centers as a city transportation, and transportation to and from the ports as freight. The overall benefits of the hub are summarized in this panel, and they are expected environmental and community benefits that directly address the cost savings in healthcare and the jobs that are created, and the actual numerical expression of the individual production capabilities at the hub. With that, I am right on the 3 minutes before the hour, so I will give you some time for transition. And I know that I have some time for question and answer session, isn't it?
Yes, yeah, correct. So I just want to thank you so much for that lecture. And now it's time to begin our Q&A session. So just a reminder to our online audience to use the question icon to the right of your screen to ask questions. It's also a moderated format, so once questions are published, you can see them and upvote them to the side, and I'll do my best to select a broad range of questions. We have a few that have come in already during the lecture, so I'll start off with those ones. Our first question comes in from Scott. Scott asks, does your work have a tie-in at all with methane capture and conversion? A more difficult emission to gather, but just as important for GHG reduction.
I know, but I don't.
No.
I mean, I had a relatively broad portfolio of researches through my life, but I was never affiliated in any way and form to the natural gas people and lobby and money and funds. I am a water electrochemist.
Perfect, thank you. We have another question coming in from one of our viewers. They say, hi, Dr. Atanassov, really appreciate the knowledge you're sharing of practical solutions in utilizing this technology. Once/if the long-haul transport industry adopts hydrogen as a main energy source, it is probable in the long term that due to economy of scale, the cost of operation and ownership will become more viable for personal transportation vehicles.
Probably no. Because our colleagues who do lithium batteries are fantastically talented. And then the colleagues who do development of grid and renewable grid development, so they're tied with the battery complex, they will do a very good job in electrifying the fleet from the bottom. I think hydrogen cars will be a nice addition to it. They will have enough fueling. I don't see them being more than 10-15%. What's very important is to notice that as we're coming out of the age of petroleum, we will have multiple sources of energy and power. The same as in the 17th century and 19th century, people did not rely only on gasoline. They will ride horses and sail the seas on wind and mill things on wind, and they were perfectly comfortable with that. Now, our generation of our kids will also be very comfortable of using variety of fuel sources rather than single one. 20th century was actually the unusual century of being dominated by a singular energy source.
Thank you. And our next question asks, can you please comment on the current state of reversible hydrogen fuel cells and their potential application for remote communities for renewable energy storage? And are you aware of any units that are available now or in the near future?
As a scientist, I love them. As an engineer, I think they're stupid. It's easier to make a fuel cell, very efficient, an electrolyzer, very efficient, put them next to each other and operate them intermittently. It's the same as the artificial leaf, which was a huge waste of public money, like the so-called photoelectrochemical generation of hydrogen. It's much easier to make a photocell, a photovoltaic device, and put it next to an electrolyzer device and just make hydrogen out of that electricity than just put everything in one device. So as an actual practical engineer, I think there is no need, unless in very special applications, like in space, explorations, when the footprint is very small, some marine applications, that I see. But in domestic, if you have high power and energy density, you put two boilers next to each other and you like boiler size units and you live happily ever after. That's my personal opinion. I'm sorry to be such a harsh person on this, but I'm known for as a person with a very strong opinions.
No, that's wonderful to hear. Academically,
it's super nice to study, reversible reactions and all that stuff. But the truth is that the hydrogen oxidation and evolution is a truly reversible reaction. But oxygen evolution and oxygen oxidation are just opposite reactions. They require different catalysis. So integration of these two processes, OER and ORR, on a singular material is non-trivial. And you most likely will be able to do that at a high temperature, let's say solid oxide fuel cells and stuff like that. So whenever you have solid oxide devices, you can operate that. For low temperature, it's totally useless to invest money in this. Sorry.
No problem. Our next question comes in from our viewer, Matthew. Matthew asks for the electrocatalytic hydrogen generation plant in California. Are there concerns with freshwater consumption, especially during droughts?
Yes.
And is there a way to use salt water as feedstock?
Yes. No. Yes, but we will not going to do it now. So for the next 8 years, when we can oversee things, we have a hydrogen generation balanced with places when they divert water used without any effect on the population. Now, with the future development, one can use desalination from the seawater or brackish water and use that for generation. That is possible. It adds cost, but at this current moment, the cost added is less than 10% technologically. Same thing, having two different devices to operate. Desalination unit by reverse osmosis next to an electrolyzer. Again, there will be people who will propose to you to make direct electrolysis of salt water. Extremely difficult to separate chlorine evolution, oxygen evolution. You will die doing that. And wonderful scientific process to study, and absolutely stupid engineering idea. Make desalinator and make electrolyzer. That will be addressed. It's been already addressed in environments that are much more demand-driven, like State of Israel and in Saudi Arabia projects. Yeah, and that's what they do: separate units for desalination, followed by electrolysis.
Thank you. Our next question comes in from our viewer, David. David asks, understanding that the focus of your work is electrochem and chemistry. Having said that, regarding desalination and desalination systems, can you comment on order of magnitude power requirements to facilitate the process?
Yes. This is a sister technology that I'm not developing myself, but I've been kind of observing. It's extremely powerful, very much needed. It's materials dependent, and of course it's extremely powerful consuming. power consuming. We know that if we combine it with continuum sources of power, like nuclear, or with power that is in excess, like a solar and wind in given locations, we can have a relatively efficient desalination. It is not a universal address, so there is some sort of a combination between the places when there is no water is usually sunny, and it could be very windy, so we can run on that coincidence. And if that is not available, then nuclear power.
Wonderful. Thank you. Our next question
Sorry
is...
for the green people, you know.
Our next question is from Turab. They say, hello, Dr. Atanassov. Thank you for your incredible and inspiring presentation. How easy would it be for current/existing natural gas production, transportation, and consumption to pivot to a hydrogen model?
The plain answer is I don't know. I have opinions, thoughts, and observations. They are legislative drivers, they're community drivers, and they're also technological drivers. I think a confluence of all these drivers will make natural gas producing companies move in that direction. We observe this locally here with the SoCalGas, which is a company that is officially dedicated to moving towards hydrogen. And they are actually distribution companies. So for them, distributing hydrogen or distributing natural gas is pretty much not the same, but not that far away. Now for the methane producers, natural gas producers, the actual dilemma will be a different to solve. I moved from New Mexico to California in order to avoid answering that question. Otherwise, I would have moved to Texas, which I didn't. Can I just have the humor here about that? I really don't know everything. And it's okay if somebody tells you that they don't know how to do it. But I can tell you that there are fantastic people smarter than me in Texas that are trying to answer that question. It's just not me.
No problem. Thank you. We have another question coming in from one of our viewers, Fiona. Fiona says, Dr. Atanassov, your work is simply fascinating. Thank you so much for sharing. And then their question is, what other areas of the world are working on this type of innovation? As a global company, I'm interested in such developments outside of North America.
Thank you. So actually, North America has been technological pioneer for this, and that includes Canada. Canada has an amazing contributions on both sides, through Hydro-Quebec on the east and everything around the Canadian National Research Council in Vancouver. Canada has a disproportionate amount of electrochemists in a positive way. And actually, they're so good. I mean, I cannot think of a weak electrochemist in Canada. The whole community is amazing. North America is technological lead, but the first implementer is Japan. And in Japan, the technology was developed very steeply because of the natural limitation from sources. Every single whiff of gas is being brought from Australia on a ship, as you know, through the Molucca Straits. And their limitation of the natural resources made them super thrifty, and they started looking into hydrogen because they are a manufacturing society, the earliest on. Their technology was supported by NEDO through about 2 decades, and that's why you see Japanese cars and Japanese trucks with the fuel cells already on the market that you can buy. You can buy a Mirai, I can buy a Mirai. And then Korea is a similar market, also limited from outside resources. So essentially, South Korea, and Japan form a similar type of markets that are extremely dedicated to manufacturing and extremely constrained by resources. And that makes them the super important firms. Then comes the European Union. European Union has extremely powerful manufacturing economy as a domestic economy in Germany and in France and in Italy, especially northern Italy. And this hardcore economy is not transportable. It is not outsourceable because of the social fabric of the communities. You cannot outsource it to Mexico, like America does, or somewhere else. They are super committed to new technology and to hydrogen technology because it presents like a local consortium of all three sources. The Greens love it because that justifies all their commitment to a new technology in renewables. The labor loves it because it creates new jobs, and the Christian Democrats, or the right in Europe love it because that essentially creates new manufacturing technology and economy. So that creates in the European Union a market for hydrogen economy that is both large and dynamic, and then with a horrible war in Ukraine, that was even solidified because now they have to deal with that without the Russian gas. So if you remember the future energy like a new tract in Europe called Next Energy Consortium. Next Energy Vision was created on the 8th of May, only a month and a half after the invasion. So practically anything that was done by natural gas can be done by hydrogen, and they will move to it also for political reasons. In China, the major driving force is environmental, pollution omission. They have a directed economy, and they also dedicated equivalent of 30 to 35 billion dollars for a 5-year plan that started last year in November with their 20th Party Congress for their whatever next, is it 7th or 8th 5-year plan. So the rate of spending in hydrogen economy of the American cluster, European cluster, and Chinese cluster in economy are similar, and the sizes are similar. They're in the region of about between 25 to 30 billion dollar equivalent, and spent over the 5 to 7 years of land. European Union plans in 7-year cycles, China plans in 5-year cycles. America doesn't plan, but the natural cycle is like a 4-year because it's related to the presidency, and the cycle in the United States is less formal but more dynamic. And every society creates different ratio between incentives and direct dotation or other. The monetary mechanisms and command mechanisms are different, very different. But what startlingly looks like these three domains and the smaller domain of economically smaller of Japan and Korea have per capita approximately the same rate of spending for hydrogen economy for the next 10 years in commitments. So it's unavoidable, and Canada will do the same. It's just unavoidable. You have manufacturing industry. You're integrated with the North American cycles with many of the American industries. Your energy systems are integrated. You're in. Whether you have a national policy or not, you will be. That's just the law of the land. That's how it's going to be. Yeah. I don't know whether I answered the question explicitly, but these are, and if this person is asking about laboratories and scientists, they're amazing scientists throughout the world. I just need to close my eyes and for 15 minutes recite names and locations, but anything that you can think of, from Edinburgh and Imperial College and Bristol, and then going down through Nantes and Paris and Montpellier, and an amazing constellation in Grenoble and in Milano, in Munich and in Berlin. You can actually go a roster of cities, and including in Canada, with a fantastic effort in Vancouver and in Toronto, and in Queens and in Waterloo. So there are and of course in Alberta as well, in Calgary. There is a very nice cluster of scientists in Calgary to do these things. It is a world effort.
We do have one more question that has come in,
Okay.
so I do want to ask it, although we won't be able to see you answer it, but we can hear you. So this next question comes in from our viewer, Emily. So they say, Dr. Atanassov, thank you for sharing. I've heard that part of carbon capturing during hydrogen fuel production is pumping/keeping carbon deep in the ground. Is this true? How will it impact desertification and agriculture in California? And what are other ways to capture carbon?
So in California, we do not plan to capture and store carbon in the ground. There are projects like that. This is in the area of National Energy Technology Laboratory, and there is a whole division of carbon capture and sequestration in Department of Energy. I don't work in those areas. Again, these are, let's say, these are projects that I don't participate, mostly because I don't fully believe in. I believe in carbon valorization as opposed to sequestration. So I prefer to study and introduce and promote technologies that the carbon that is being captured from CO2 is turned into polyethylene, and turned into caprolactam to make nylon and to make things, to repower essentially the chemical industry. And I know that the biohydrogen produces carbon like a char, black carbon. I still think that it can be used technologically for construction and for other components. Making just carbonates and putting them in the ground, I don't know, maybe we will live to those amounts of CO2 that we capture to do that. I do not contribute to that technology myself. Again, I will tell you that I don't fully understand it. It means that at this moment, for my own generation, I don't fully believe it. I prefer to make things that are useful. So that's the difference between carbon sequestration and carbon valorization. These are the two terms that are used by two parties, let's say. One that say, let's remove carbon and put it away in a drawer, and the other say, well, let's put it back into the chemical industry and make things that people can use and enjoy.
I do just want to take this time again to thank you, Dr. Atanassov, for your time and for delivering such a wonderful lecture to our group and for taking the time to answer our questions. I also want to thank all of my ATCO colleagues who have helped put this event together for today and for everyone who's taken time out of their day to join us. We very much appreciate your interest in the speaker series, and we invite you to keep an eye on our social media pages for future ATCO SpaceLab Speaker Series events. So we do have one upcoming, and that will be September 20th with Professor Stephen Bethard from the University of Arizona. And with that, I just want to thank you again to our lovely presenter, and I'll conclude the session for today. And yeah, everybody,
Thank you very much.
You enjoy
Thank
your
you.
Friday.
It was a pleasure for me. It was a pleasure of mine. Thank you so much. Appreciate it.